web. So, Konsta, most welcome.
Thank you, Monica, for the introduction. Share my screen. See the slides.
Konsta, it's kind of hard to hear what you're saying.
Is better now?
Yes,
Okay,
thank
good.
you.
So you can see my slide now.
Yes.
Okay, excellent. All right, so good morning all. My name is Konsta Sipilä, and this first presentation of today is about joint sealants in nuclear power plants. This is a rather new study. We started doing this in the beginning of this year, and the motivation behind this study is that we would like to know a bit more about these joint sealants, what exactly are used inside nuclear power plants, and what type of sealants they are, what materials, and what are their aging mechanisms, and how you could monitor their condition. So this is just a brief introduction into the topic, which is not that well known, at least our point of view. So the content of the presentation, I will first go through a bit more detailed information about these joint sealants, what they are, then about the environmental stressors that they are facing inside nuclear power plants, then aging mechanisms, and what are the most suitable testing methods for such sealants. Then we have obtained some materials from TVO last outage. I will show those materials, and then a little bit of future plans, what we are going to do next year. So joint sealants, they can be defined as polymeric-based materials, and they are usually applied between a group of two structures. And this polymeric material adheres these two separate structures tightly together, so that no moisture or gases could penetrate through this sealed area. Quite obviously, these kind of sealing solutions are quite integral part of each building or construction, and the components that these polymeric-based sealants are applied, they include a wide range of materials: concrete blocks, wall elements, glass structures, metals, and so on. And commonly used materials that are used in constructions. These joint sealants, they are commonly used in various type of structures because they are rather easy to use, and currently you have a quite wide range of different types of polymer sealants and different kinds of applications that you can use these sealants. These are also widely applied in nuclear power plants, but currently, at least to our information, there's not much knowledge what exactly these joint sealants are that are used inside NPPs, and how we could monitor that condition in nuclear facilities. We can classify these joint sealants based on their properties. Typically, they are classified by their material or elasticity, or in which form they are applied. Well, before 1950s, traditional caulks has been actually applied, which are based on oil origins such as linseed oil, bitumen, or tar. But in the 1970s, these industrial manufactured polymer-based materials replaced these traditional sealant materials because they were simply had better material properties, and they were easier to apply. And nowadays, you have a broad range of different type of polymer-based materials available for these joint sealants. Here we have a kind of a summary table on different kind of joint sealant materials that is available from the markets. 8 different type of polymer families, and they each have slightly different properties and slightly different applications that they can be used for. So perhaps the most important view or a thing here is that how the sealant bonds to different substrates. So not every polymer family is applicable for example metals, and some other polymer is better to be used with concrete structures and so on. Then we have a rather large temperature range where we can use these polymers. For example, acrylic-based polymers cannot be used in rather low temperatures. On the other hand, when you compare it to silicon, for example, that can be used rather wide range of temperatures without losing its flexibility, for example. Then different polymer families have different kind of resistance towards moisture, and that's why basically in household use you should buy a certain type of joint sealant material if you plan to use it in the kitchen or in your bathroom. And then one point is that whether you can overpaint the used joint sealants. For example, in silicone-based joint sealants, you cannot overpaint because the paint won't adhere to the silicone. Then about the environmental stressors. Basically, with joint sealants, the weather changes are the most relevant one, which causes the aging, because there is rain, ultraviolet light from the sun, temperature changes. These are rather extreme in outdoor applications, but now we're looking indoor applications. These are also present, but clearly in lesser extent. Inside containments, we performed a study a couple of years ago regarding the Finnish nuclear power plants, and the conclusion from there was that there's, for example, inside of containments, you have always temperature less than 50 degrees. And in nuclear power plants indoors, you don't have these heavy temperature cyclings that is present outdoors, for example. And then you don't have the presence of these thermal expansions in structural elements, at least in that high extent. And that would cause the absence also the cyclic mechanical loading, which the sealants will face in outdoor applications. Maximum dose rates, they are inside containment, they are less than 1 gram per hour. But the sealant materials are not typically located in the vicinity of these radiation hotspots, so they face significantly smaller dose rates, and this was actually backed up by the data we obtained from Olkiluoto materials. The effect of water in joint sealants, this is due to moisture and humidity. So moisture is basically water which is contact with the joint sealant surface, and moisture is humidity is then related to the water vapor pressure in air. And it seems that the temperature would be also in this case the most significant stressors that the joint sealants are facing inside nuclear power plants. Then about the aging mechanism, we have identified so far three of which the joint sealants are facing. First is the oxidation. This is due to the interaction of matter with either thermal movement or radiation, which cause the formation of radicals in the material. And these radicals further react with oxygen, forming peroxide radicals. And these peroxide radicals can abstract hydrogen atoms from the surrounding molecules, which causes formation of hydroperoxide and then further more radicals. The decomposition of this hydroperoxide will can cause either a non-radical or radical species. So this oxidation process is kind of a self-sustaining type. Then we have evaporation of plasticizers. So plasticizers are typically used in polymers to make them less stiff. So when these plasticizers are evaporated from the sealant, they turned out to be rigid or stiff. So the evaporation, the mechanism is related to the plasticizer migration in the material to the surfaces, and then followed by the actual physical phenomena of evaporation. This is a rather complicated phenomena, and it's affected several things. Firstly, material properties, both the polymer and plasticizer, and then of course plasticizer concentration, and then some external properties such as temperature and the surrounding atmosphere. Then third, we have water absorption. So the hygroscopic materials, they can absorb moisture from the air, or which is condensated on the surfaces. And water also has several accelerating effects to the aging. Mostly it increases the mobility of the different molecules in the polymer. It can decompose the hydrosoluble groups. Then you can see reversible increase in plasticity due to the ingress of water, and then the water can cause also leaching of water-soluble ingredients. So that can be either good or bad thing in aging perspective. Then we look into the testing methods which could be applied for this type of sealants, and here we have identified 5. The first one would be tensile test, and as it is well known that the elongation break is well established aging indicator, but here the issue is related to the sample removal, because tensile tests require a rather large amount of sample, and the reality is that the dimensions of these joint sealants, they usually aren't that wide, despite they are long. So you really cannot remove any samples without destroying the actual seal. So here the applicability of tensile test is limited only for the surveillance samples, if such are even available. Then we have hardness measurements. It can be considered to be non-destructive, especially if the indentation mark is not too severe. And hardness is good measurement method because it has been shown to be correlate quite well with elongation break values with several polymers. However, the hardness measurement is sensitive to few factors such as temperature and how you clamp or attach the measuring device around the sealant. Then the applied force and intended tip. But most of these factors are such that you can minimize their effect by using standardized methods. Then we have a density measurement. Usually the aging increases the amount of oxidation products in polymers, and that has an effect to the density of the material. Also, the evaporation of different volatile species from polymer can cause changes in weight, dimension, and density. And density measurement also requires sample removal, but the sample amount is relatively small, so it might be applicable in this case. Then we have the gravimetric analysis. In TGA, basically this sample is heated in a predetermined atmosphere, and the weight of the sample is measured simultaneously. And it is good method since it also requires only a small amount of samples. And it has been previously used analyzing volatile compounds from coatings. From a standardized method already exists for this. So that's why we found this method to be interesting in joint sealant studies as well. Then finally, we have the photon transport infrared spectroscopy. So here, the basic principle is that each oxidation product have characteristic wavelengths, and they absorb infrared radiation, which enables identification of these oxidation products. And this FTIR also requires sample removal. Then we have the materials that we have obtained from TVO. This outage was last May and early June, and it covered both Olkiluoto 1 and 2 units. Basically, what we received samples, we had two types of sealants, trademark from Tiotat and Sikaflex. And most of these samples were from the original installations. Here you can see this is in Finnish, the heading here, but here you can see the temperatures, and all temperatures at which these sealants were exposed, they were below 30 degrees. The atmosphere was air, and dose rates, most of the samples didn't see any dose rates, and those which saw some radiation, the dose rates were very low. So the maximum annual dose calculated from the highest dose rate was about 0.4 grays. So this is a clear indication that the effect from the radiation is rather low to the aging of the sealants. Then about plans for 2022. What we're going to do next, we're starting to work with the samples we received from TVO. So we try to identify what type of polymers they are actually used in there, and then analyze their condition. I think we're at least doing hardness measurements, and TGA also seems to be tempting, since it has been already applied in the case of coatings. And then we also have information about the newly installed sealant, which replaced these removed ones. So it was polyurethane-based Sikaflex sealant. So we are planning to do a small test matrix also with that material. Perhaps perform thermal aging and provide hardness and TGA. And then based on these results from the thermal aging, we could try to provide an estimate on the lifetime of this type of sealants, how long it would endure in the plant use. So to summarize, in the modern constructions, various types of polymer-based joint sealants are applied, and they are exposed to different types of environment stressors, and the temperature seems to be the most relevant one from the aging point of view. Aging mechanisms that the joint sealants are exposed in indoor use, they are typically thermally induced oxidation, plasticizer evaporation, or water absorption. Different types of testing methods are available for these joint sealants, but currently only the hardness measurements could be considered a suitable method when non-destructive analysis of these sealants are considered. Then we continue in sample next year to evaluate these materials that we have received from Olkiluoto, and we try to identify what type of materials these exactly are, and also for the newly installed material, we try to estimate how well it could perform in the designed application. So I guess that was all from this newly started study that we are currently doing. If you have any questions, please feel free and ask.
Thank you very much, Konsta. I think this is a really interesting study. And I was wondering, you mentioned overpainting. Is it sort of smart or not smart to overpaint?
Well, basically, the benefit from overpainting is that you kind of insulate the sealant from the outer atmosphere, and in the outer atmosphere you have oxygen, so it will decrease the ingress of oxygen into the sealant, and it kind of protects it from oxidation. So it might be a good thing to paint it.
But I guess that you need to be careful when choosing paint to make sure that it's not like a harmful reaction.
Yeah, and it will stick to the sealant.
Okay, we have a question first from Anneli Jansson. Please, Anneli. You need to unmute, Anneli, if you're talking.
For that. Regarding, I can imagine that you probably will have a gradient in the material here. If you're looking at the evaporation of volatile specimens and oxidation products and so on. When you're taking the samples, I think I see that it could be a problem to get representative samples.
Sure, that's a
what do you think about that?
Yes, we have the sample dimensions here, but I think this is I need to check actually the thickness of the sample. That's a good point. And for this purpose, we should do some kind of cross-section analysis also for the sample just to check how homogeneously aged the sample is exactly. So
yes, yeah, and I can also think that if you're taking the samples on the surface, it probably will be different from the rest of the material.
Yeah.
And so these samples from TVO, is it from a replaced sealing? Because you damaged the sealing when you're taking the samples, otherwise I guess.
Yeah, these were all the samples they had. I'm not sure whether there's someone from TVO here to comment this, but they actually removed and replaced all of these sealants. So you put a new sealant in the whole seam. So
okay,
so these are old removed sealants, and there are new sealants currently in operation. And we plan also to test this new applied sealant in next year, how it will endure artificial aging and so on. So, but yeah, this was a good comment to check the cross section, and I think we definitely should do that also.
Thank you.
Thank you, Anneli. And then we have Sven-Olof Palm on the list with questions.
Oh, yes. More a general question, not specific for this presentation, but you talked about radiation and the doses, and you had quite low doses. Do you have an opinion if we have thresholds values for polymers where there are no need to take radiation in account for aging? Of course, it would be different for different polymer materials, but for the material that you talk about now, for example, do you have an opinion about a threshold value where we don't need to put time and money into the aging process for radiation?
Yeah. Well, I will base my answer previous experience, what we have done with cables. So the cable materials, let's say for cross-linked polyethylene, I think you need to have tens of kilograms dose at least of tens of kilograms of dose before you can see actual changes in elimination of break values. It can be even 100 or 200 kilograms before you see any changes in good quality cable materials in, let's say, in elimination of breakage. So I think it's rather high level doses that you need to expose the materials before you can see changes in mechanical properties. So that's my initial guess on this matter. So here, when we talk about some grays, I don't see that they have significance in the aging perspective.
That's hopefully something you can verify with the testing that you are planning, and perhaps you could also irradiate some of the samples after you've done the first testing and see if
I
the
think,
properties have changed.
Yeah, I'm not sure whether VTT has still the gamma cell. We will have the low dose rate radiation possibility. I'm not sure whether it's still functioning, but if it is, we can do the small dose rate radiation. We're talking about some tens of grays per hour, so really low dose rate radiation. So
because it's a quite interesting topic for the nuclear industry due to that radiation aging is quite costly and it complicated the process. Usually the labs don't have it in-house. They have to send the objects away, and we have a supplier that even though we say that you don't need to irradiate it, it's clearly not a parameter that is important. They say that it's a point in the qualification standard about irradiation aging, and we need to perform it even if it's not necessary, and it gives us cost and time problem.
I also recognize this issue, and it is good that it is discussed, but also my perspective is that during normal use, the thermal aging is what dominates regarding any polymeric material. So in accidental scenarios, that's a different story. There you have high doses, but for normal use, when you qualify things, I think in most cases the thermal aging is the one that dominates.
Yeah, I think it could be good for the industry if we could, through this work or something else, we could have a statement that we generally, if we are on the level of a couple of kilograms, we are not needed to do it if we don't have a specific Teflon material or something that are very accessible.
Yeah, that's true. And I think that Teflon is one of the few materials that it really is susceptible to radiation aging. But the others, traditional cable materials, they are quite well radiation resistant. So,
is there anything found in literature on this from previous tests?
There you could find thresholds value in some literature and so on, but to go from that to a statement that you don't need to do the radiation aging, it's still a step, a process to go. At Forsmark, we haven't performed any operation dose testing on polymer material during the last 4, 5, 6 years or so. We have stopped it, but when we talk about qualification, when a supplier write a qualification program, they always put it in, and we have a project now there they say that we need to do it because our internal instruction says that we should do it from the supplier's point of view, and we try to convince them that you don't need to do it. You don't have material that are acceptable for radiation aging, and so we need to pay for something that we don't want, actually.
Thank you. A final question from Mauri Takala.
Yes. I just have a quick question. This material is obtained from a TVO outage. Which positions have you focused on to take those samples?
They were actually quite various positions taken on different rooms and so on. So there's not a single application. So there are several different positions that they're taking. Actually, you can see from this table that there's quite many different locations where the sample has been removed.
Yes. Okay, so it's nothing through the penetration, but the different locations.
Not I know about
Okay.
penetrations.
Okay, thank you.
I can confirm that, yeah, later.
Thank you very much.